Is 2:35 and time to get started. Our next speaker, Frank Stratton, likes rock climbing and developer tools.
Thank you. Thank all of you for being here. So my talk is about smart services and smart clients. Basically, how we at Runscope build microservices and deploy code. So I'm Frank, CTO and co-founder of Runscope. And just for a little bit of context, I want to tell you kind of what Runscope does. So we build tools to help developers solve API problems. One of those tools is called Runscope Radar. It's a way to build automated tests and monitoring for APIs. And the idea here is that you can chain together a series of HTTP requests into a test, and then extract data from those requests and use them as variables in following requests. You can write assertions on the responses that come back, basically letting you know that APIs are up and running and returning the correct data. The other tool that we have is our traffic inspector, which allows you to capture in-flight HTTP requests, and it gives you this real-time stream to help you debug any API problems between your client and the APIs that you're using. So it'll give you detailed request and response data, as well as status codes, timing information, and all that kind of stuff. So that's the tools that we build. And to do that, we have over 60 services now that are independently deployable, but only an engineering team of 8 people. And kind of very early on, we had this kind of very intentional goal to build lots of small services. In the last year or so, the hot buzzword is microservices. But this was a very conscious decision for us. And part of that, you might ask, is just why? Why have all of these moving parts, all this complexity, even when you have just a small team of 2 people or 5 people or 8 people? And so for us, the answer to that was really about both scaling the infrastructure, being able to handle the growth of our company as we grow, as well as scaling the team and making sure that our processes and our way of developing software can map to the teams and the coordination and the amount of kind of overhead that comes with growth. So a lot's been said already about microservices, what they are, how they work. There's a lot of good talks, a lot of good articles out there. So this talk is really, we'll touch on kind of some of those things, but really I wanted to focus on kind of how we do things in practice, what technologies we use, and how we kind of organize our code to make all of this work. So just kind of a high level, one of the reasons why we chose this architecture was that microservices kind of by definition are highly independent small components. And for us that means both independent code bases, independent deployability, and then having different teams own different parts of the stack without having to coordinate between each other. Needless to say, that means there are a lot of moving parts. You've got a lot of different things changing, a lot of things being shipped to production all the time. And it takes a lot of kind of work to make sure that this works smoothly and doesn't fall apart. So I think the biggest lesson that we've learned over the last 2.5 years for running microservice architectures is that if you don't invest in infrastructure, don't invest in microservices. Another way of thinking about this is that a microservice architecture is taking kind of this decade-long idea of what a traditional service-oriented architecture is and applying that with a heavy kind of DevOps bent and really applying a lot of automation and infrastructure tooling around that to make this all possible. So to get into some more kind of concrete examples, kind of in the beginning, we had our dashboard, which is our website. And then we wanted to build another service to encapsulate all of our customer data and kind of give us kind of a data access layer. And so we call that service identity. And identity lets you get things about customers, about teams, and kind of just generally put and get configuration data. And so kind of in this world, we've got these 2 services. One of them is living on host 001, and one of them is living on host 002. Now you start to wonder, like, how do I actually implement this function, get teams? Right, so the most straightforward way of doing that is, hey, we'll just use requests. We'll just import requests. I'll just build a URL to host 002/teams, and then I'll do a GET request to that, and then just return the JSON that comes back. OK, so now this is code, and it works, kind of. So the tricky things here are when you start to talk, when you're going from like a monolithic code base to this service-oriented architecture, is that things are always kind of changing. Hosts that you spin up and run, sometimes die, and you have to change and replace hosts. So for instance, what happens when you migrate from host 2 to host 3? Well, now you've got to change your code and deploy that just so you can address that new service. Kind of a bigger question here is what happens if you have multiple environments? So if you've got a local environment, a testing environment, and a production environment, all those things need to talk to different hosts, whether it's your local host, whether it's your test cluster, or whether it's your production cluster. And so kind of hard-coding these host names turns into a kind of a big mess. So we wanted to avoid all of that. But really, the first question that you have to answer when having all these services is just how do you find a service? So our answer to that question was something we called Smart Client. Smart Client does a few things. So first, it's a wrapper around Python requests. So you can just drop it in wherever you use requests, and it just works. So it handles, it has the same API and gives you the same response objects. So the next thing is that instead of kind of hard-coding all of these different host names in our cluster, we wanted to go a different approach. And that was to kind of invent something called service URLs. And so Smart Client accepts these things that look like HTTP URLs, but aren't really. So it starts with service : / and then the name of a service. So the nice thing about this is that this service URL works in your local environment, in your testing environment, and your production environment, and you don't have to change or update any of the code to make that happen. So Smart Client really does kind of three main things for us. One is just that service discovery layer. So being able to translate that service URL into an actual service host name at runtime. The next thing it does is it will automatically retry, get, put, delete requests, just in case there's a temporary network outage, or if you're load balancing across lots of backends, and one of those requests fails, it might succeed on the next one. The other nice thing that it does is it has an option to let you run requests asynchronously. So if you have lots of service calls that you need to make kind of in parallel, you can fire them all at once and then wait for all the responses to come back. And so you're not kind of blocking, waiting for each one of these in serial. So now the question is, how does this actually work? And where's the mechanism that's powering all of this? And for us, the answer to that question is also a service. So we have a service called Atlas, which, if you can maybe guess, contains information about how our cluster is mapped. So Atlas stores information in DynamoDB and Zookeeper. And we basically say whenever a new service is created, or whenever you attach a service to a particular host, we record those bits of metadata. And for instance, in Zookeeper, we have this kind of directory structure where it starts off with hosts, and then the service name, and then the actual host name that service is running on, and what port it's running on, and whether or not it's enabled or disabled, and kind of all of that stuff. So that is really a service that encapsulates all of that cluster configuration. The next part of this is a Python daemon we call sidecar. And sidecar runs on every single host in our cluster and does a few things. So first, it runs a copy of HAProxy locally on each of those hosts. And then it configures HAProxy by reading data from Atlas. And then once it's done that, it sets up Zookeeper watches on those keys to know if you've enabled or disabled a host or a service, or if you add a new host or a new service, those changes will kick off a reload of HAProxy. So what in effect happens is you've got this cluster of machines, and sidecar and HAProxy are running on each of them. And whenever you need to make a service call, you're actually taking that service call and making it to localhost. And that localhost service call gets fanned out to service A, wherever it's living in the cluster at that time. And then if you want to talk to service B, you address localhost, and it goes off to service B. So that makes the actual implementation of what Smart Client is doing pretty simple. So it takes that service URL, parses out the service name, and then uses a custom header that we've added called Runscope service and passes along that service name. And then the actual request is made to localhost and then the HAProxy front-end port. So the interesting thing that we're doing with HAProxy is we're actually using a feature called ACLs, where you can actually dynamically route a request based on information that's coming in that request. So here, you can see we're binding to one port 4000 in HTTP mode. And then we're constructing an ACL called host API, and we're doing a pattern match on that Runscope service host header that we've added in Smart Client. And if it matches API, then we're going to set that ACL, and then later on in the configuration, it says use backend API backend if host API. And so we basically construct one stanza for all of our services, and then kind of dynamically at runtime, based on what header is present, it will choose the appropriate backend. And those backends were also configured with the current state of the cluster from Atlas. So that makes the implementation of this really easy, and the kind of biggest benefit that we got from doing it this way, because when we originally built Smart Client, we had a lot of hard-coded service names and hard-coded port numbers and kind of lots of information that we knew, but that was all kind of baked into the library. And so whenever we would add a new service, you'd have to update the library, do a new build, and then deploy all the services that used it. Moving to this kind of HAProxy dynamic header routing, it's all kind of data-driven now. And now instead of doing a code deploy to pick up a new service, it's just adding a new line in a database, essentially. And so the code for Smart Client now is pretty static, right? We've gotten it to a good place, and we don't have to do new builds of it. We don't have to do new deploys just to pick up kind of new services that get added to the cluster. So that's kind of the first question is, how do you find a new service? The next question we had to ask ourselves is, OK, how do I make service building really easy? And our answer to that, unsurprisingly, was called Smart Service. So Smart Service is a library that's built on top of Flask and Flask RESTful, a Flask extension to help build REST APIs. And then we've kind of started with this base and started adding more and more packages on top of it to kind of bundle together a lot of common features and functionality that we found we needed. So one of them is an open source project that we have called Health Check, which makes it easy to add health checks to Flask apps. The kind of next bit built on top of that is a set of either third-party packages or other internal services or libraries that we've written to kind of deal with a lot of boilerplate code. So we use Bugsnag, a third-party tool for doing exception logging. And then there's a couple projects that we have called Runscope daemon, which makes daemonizing processes and running asynchronous tasks really easy. And then Alchemist, which is our library for doing kind of database connection setup and teardown. And then the other bit is smart config, which kind of works together with Smart Service to replace something that we were doing kind of from the very beginning, which was kind of dealing with hard-coded constants and API keys and other configuration things. We would just kind of dump those into a Python file and say, hey, from config, get config.redstdb, and use that all throughout our code. Well, when we built Smart Service, we wanted to keep that kind of interaction because it was very easy and very kind of predictable to know, like, OK, I need to find this API key, or I need to find what Redis database I'm using. It was all kind of located in one place. So then we built Smart Config, which basically lets you load that config module directly as a set of defaults. The other thing Smart Config does, though, is it actually can query Atlas at runtime and get other variables and overwrite those defaults if you need to. So that's really helpful for not putting secret tokens into your source control and checking those into GitHub, because you can leave either empty placeholders or just not set those variables in your source at all and have that come from Atlas via Smart Config. So the other thing here is that we're initializing Smart Service and we're passing that config object into it. And the thing that we get out is an app object. And that's basically a wrapped Flask app. So it has all the things that a normal Flask app has on it. But based on the values of that configuration that we pass in, we get a lot of extra properties on that object. So you can always, no matter where you're at in your code, from Flask import current app. And then use current app.realm, which will tell you, am I in my local dev environment? Am I in our testing environment? Am I in production? It has things like, if you specify a Redis DB in that config, it will automatically construct and put a Redis client on the Flask app object for you. So you don't need to know, do I need connection pooling? Do I need, what host name does it map to? Where do I route this request? As a developer, you just say, oh yeah, just import the current app, get the Redis client, and start using it. The same thing for database clients if you've configured Postgres. And then it has the Flask RESTful API object. So you can just go ahead and start adding new routes to your service. The other thing that Smart Service does is it kind of builds this common logging configuration. And so once again, everything is pretty standardized. We put everything in one location. We configure our log formats all at once. And so as a developer, you don't have to think, how do I access the logger, or how do I construct the right format, the right output format for the access log or the error log, or if I'm using Bugsnag to notify notify an exception has happened, you just kind of import those things and just use them. And this is kind of building consistency across all of our different services. The other bit that we have with Smart Service is this idea that we can auto-generate these service skeletons. Since all of our projects kind of look the same now and behave in the same ways, we can actually just run one command, generate service, and that will build a lot of things for you. So it handles all that boilerplate of constructing a new Smart Service object, doing kind of default values. It gives you a directory, a Git repository, a virtual environment, and all of those requirements installed into the virtual environment. So what, in effect, you have is you run one command, and then a minute later, you have this fully operational service that you can take and you can deploy it right away. And so it's kind of gets all of that overhead of how do I get started, how do I set something new up, and it kind of reduces that into a single command, and now you can move on and actually write useful code. And so Smart Service and all the things that we put into it, as well as Smart Client itself, kind of go into this idea of reducing cognitive overhead. The amount of things that you have to think about, or the amount of times you have to context switch from, okay, so I need to access a database, but where is that database, or how do I construct a new SQL Alchemy model, and then where do I find the database session, and what do I do when the app is done with this request? Do I have to tear it down? And all these things, they're kind of answered for you. And as a developer, you just say, hey, database, do this thing that I want, right? And then move on to the next thing that you want to do. So this is really helpful for managing lots and lots of services, because all of these services look and behave and act the same way. If you fix a bug here, and then you need to context switch and move to another project and implement a new feature, all the logging is the same, all the database handling is the same. You don't have to think about those little details. You can focus on writing actual code. So that's kind of what we did to make building services really easy. And so now we have a lot of services. So the next question is, what happens? Right? So a lot. So the next bit of this talk is about some of the lessons that we've learned, or some of the things that we've decided to kind of bake into our process to make living in a world with lots of services really easy. So the first lesson, not surprising, is you have to automate everything. For us, that means setting up new servers when we bring them online. That means we use Puppet to kind of generate templates for all of our init scripts, all of our monitoring. Kind of everything that you do has to be kind of repeatable and kind of deployable without having to think about it. So you have to invest a lot in DevOps, and invest in kind of automation tools and scripts to make running 60 services, making 100 services kind of reasonable. The next thing that we kind of learned is that once we've built all these services and they're all kind of operating and talking to each other, and we've got all these nice and interesting tools, is that you actually become language agnostic. So most of our stuff is Python, a lot of Python services, but about a year ago we started writing a lot of Go code. And so when we figured out that kind of first bit of how do you build and deploy Go, and we had a Go service up and running, it became really easy to integrate that with the rest of our cluster. We got all of these nice features that already existed from our identity server knowing about customers, right? And so a piece of Go code doesn't need to know what format is that data in, or what database do I need, or what ORM do I need. It just needs to know, hey, I've got this API that I can call to get all this data back in JSON. And so we were able to kind of quickly spin up either new projects, third-party tools, anything that talks HTTP becomes immediately useful in the context of our cluster. So we kind of say that HTTP is our common language. Kind of the next bit was more of a kind of a philosophical decision for us early on, but it's really paid off which is there are no shared databases between our services. So we could have imagined a world where you have our dashboard, our traffic gateway, our API, all talking to the same Postgres database for customer data. The problem that happens when you have this kind of architecture is that you have this shared dependency between not only the type of database that you're actually running, but also the schema that that database has. So if we add a new column, make a schema update, then we have to deploy code to all three of these other locations. The real problem with that is that it's no longer an independent system. Right? You're taking what used to be three independent services and actually tying them together very tightly. And so whenever you have this kind of pattern where if you make one change and you have to deploy everything else in the world, you know you're doing something wrong. So for us, we said, none of this. We're not going to do that. Every service owns its own data store. So for identity, right now, we run Flask, we run Postgres. We used to run Memcache for caching. We changed that for to Redis. But the point is that from everyone else's perspective, it's just an API, right? You don't have to know what technologies are involved in that API unless you're actually developing that service. And that really kind of keeps the context small. And so if you need to know, oh yeah, this is how SQL Alchemy interacts with Postgres in the context of identity, then you can focus on that one thing. But if you don't actually care about that, if you're developing something for the website or adding a new feature to our public API, those things are kind of irrelevant to you in your day-to-day. And so it keeps that kind of mental overhead small and makes it really easy to kind of change things kind of independent from everyone else around you. Speaking of changing things, kind of the biggest effect from going to this microservice architecture for us was that once we invested in all of this infrastructure and automation, it made deploying code really easy. And this is something that we've kind of reinforced over and over and over. And it's something that we wanted from the very beginning was the idea of kind of a one-click deploy. So we built this, not surprising, a service called Prometheus to help us do deploys. So this is our kind of operational and service dashboard. So right in the middle of the page, you see a list of branches that exist for this service, and then a bunch of deploy buttons to the right. And so you can deploy to our testing environment any branch that you want at any time. And kind of at the top of the screen, there's when was the last build, what was the build status of it. So we run Jenkins to do unit testing and Pylint and PEP8 checks. And then for each of those branches, you can see whether or not those builds succeeded or failed. But the idea here is that we want to make it so simple to get any service deployed to our testing environment and to production that on your first day, you can come, check in code, and deploy it to production as an engineer. And since all of our services behave independently, each one is independently deployable, and we've kind of made this rule that once you've code reviewed your changes and merged them into master, you can immediately go and deploy it on your own. We found that people do that, and people really like deploying. And so right now we're doing over 50 deploys a day, even though we have such a tiny team. So the next question is, when you're deploying all this code, so quickly, how do you not break things all the time? So for us, going back to the products that we build, we actually use our own testing and monitoring tools to monitor our own internal services. So this is such a lifesaver for us. We're able to build kind of service tests in our testing environment. After you deploy, it automatically triggers this automated test, which goes out, verifies all the service APIs are up and running and returning the correct data, and then lets us know via Slack or via email that something is broken. And so the nice thing about the tool that we've built is that you can write one test, create variables for all the host names, and use that in your local dev environment. So you can do kind of test-driven API development and point that test at your local host. You can take that same test and run it against our testing environment and trigger that automatically after every deploy. And then you can take that same test and run it on a schedule in your production environment to know that it's up and running and that the performance over time is stable. And so the idea here is that all of these things together, smart service, smart client, our own testing tools, kind of make this graph possible. And as an engineer, like coming in, being able to deploy, being able to fix a bug in less time than it takes to respond to the support email, getting things into production constantly, day after day after day, is incredibly empowering, and it's kind of it's something that we knew was possible when we started the company, but seeing it in practice over the last 2.5 years, it's something that that we're very proud of. But at the same time, it's something that changes how you think about code, how big a feature you scope, and how often you make changes to your site, and you can do that with confidence if you invest in all the right pieces of infrastructure. So that's all the talk that I had planned. Thank you. And I think I left enough time for a few questions.
We definitely have a few minutes for questions. I thought there was a microphone for questions. Perfect. Okay, go right ahead, please.
So I had a question about how you use independent databases for all the different services.
Mm-hmm.
How do you deal with keeping them consistent when you have sort of de facto foreign keys between those services?
So we try actually not to have kind of de facto foreign keys between those services. We try to organize services around the data that they're actually storing to keep all that kind of related information together. And so a lot of things kind of assume there's a particular structure and a particular key, but we try to keep those loosely coupled between services that I have a customer ID here, and that may or may not exist, but I'll check that at runtime when I need to. But most of the data consistency where you need kind of hard linkage between objects, we try to keep that within one service.
Hi. Do you have any tools that help you debug runtime errors related to data flow between multiple services, and how difficult is that?
So one of the things that I showed earlier is our traffic inspector, and we can turn that on for ourselves and add basically add headers that get passed from service to service. And so in our interface, you can do a little search query and say, does this header value exist? And so you can tag basically a request flow as it goes from service to service.
Could you talk a little bit about high availability, like your microservices behind load balancers or anything like that?
Yeah, I didn't kind of touch on that idea very much in the talk, but since we have these small independent services, and each one is replicated across availability zones and different data centers, and we have these kind of local load balancers on each service, if a request to one of those services fail, there's always another one up running somewhere else that you can try to retry that request to. And that's kind of what we built into Smart Client, is to automatically retry requests when we know it's safe to do so.
Thank you.
During your talk, you mentioned that HTTP is your common language between microservices, and I was wondering if you had any idea of what is the overhead of using multiple microservices due to the transactions that need to happen in the HTTP layer to get the data needed to answer the customer question.
Yeah. There is some natural overhead for using HTTP. And for us, I think the thing that we want to optimize for is ease of use and kind of developer productivity. And so there is some optimizations that we could use. We could replace that layer with like a binary protocol, something like that. Kind of at the end of the day, what we found was that we move so quickly and things change so often that kind of baking in those things right now didn't make a lot of sense. The other thing that we found, though, is that with enough caching and with enough kind of asynchronous work, you don't have to worry so much about performance, but we really strive for correctness first.
Hiya. How do you deal with when services depend on each other and you're going to upgrade one and you're going to need to an upgrade? I'm talking, I guess, about API versioning.
Yeah.
So we have one service, you want to upgrade it and make it have new features because another service wants to use those new features. How do you just deal with the dependency management problem you've got there?
Cool. So this is the last question I've been told for time. But to answer your question, we try to make all of our APIs as backwards compatible as we make changes. So what we found usually is that once you've built when the API changes the most is kind of during the first development. And so we kind of iterate locally and in our test environment, and we're not afraid to break things in our test environment. But once we've kind of deployed something and have it up and running, we try to make any changes to that API backwards compatible with all the old clients. And so sometimes that might involve kind of staging releases. So you would deploy one version of the API that kind of runs in basically 2 modes, and then deploy all the old services that use the old mode and migrate them over, and then kind of deprecate and remove that old API. But we try not to do that very often.
Cool. Thanks a lot.
So if you want to ask any more questions, come find me outside the room or come by the Runscope booth. We have tons of people here talking about APIs and API testing.
Okay. Thank you.
Thank you.